In my lab, we develop microfluidic technologies, and we work on the interface between biology, physics, and mathematics. And so we do quantitative biology, where we measure very precisely cellular behavior on a very large number of cells, using physical methods that we have developed in the lab to manipulate the cells and droplets. And we use mathematical modeling in order to understand the measurements that we make. Microfluidic technologies are fundamental to our work. Most of what we do happens inside microfluidic channels, and this implies that we need all of the instrumentation that goes around the channels, from the flow controllers to the microscopes and everything that goes in between. In my lab, we use a range of different types of instruments. Fluigent instruments are particularly useful for us when we need very fast actuation of the fluids, or when we need to integrate many operations using a simple device. So in many cases, what we end up doing is combining the suite of tools that Fluigent offers in order to make complicated operations on the fluids without complicating the usefulness for the user. So one of the challenges for microfluidics is to disappear, is to become a brick that is invisible inside of a much more complicated technology that allows you to get answers that you couldn't get previously. So the first challenge, I think, for microfluidics is to disappear from the view of the user. In terms of developing new technologies in microfluidics, the integration of complex biological protocols inside of microfluidic devices is still at its beginning. I think that in the next years, we're going to see more and more complicated biology being done in microfluidic devices, much more than what we have so far.